Hey everyone, Kelly here. This video is going to go over a few of the end examples from section 9.2 and the examples from section 9.4. Our first example comes from 9.2. For a sample of 7 states, for the number of house fires started by candles a year, the mean was 7,041.4 fires with a standard deviation of 1,610.3 fires. Find the 99% confidence interval for the mean number of house fires started by candles. So we definitely want to observe that the main question is asking us to find the confidence interval for the mean, which is going to indicate the formula that we should use. The formula for confidence interval when estimating a mean is x bar plus or minus t alpha over 2 times the sample standard deviation over the square root of n. Now, in order to use this formula, we either have to have a large enough sample, so a sample of size 30 or greater, or our data has to be normal. Since we have a small sample, we can't really check that without our normal probability plot and a box plot. For our tests and our quizzes, we're going to assume normality. Now that we have our formula, we can go through the problem and identify the values. From our problem, we know that x bar is 7,041.4. The sample standard deviation is 1,610.3. N is 7. And thinking ahead, because we're going to be using the t-distribution, we also need our degrees of freedom, which is n minus 1, or 6. We know that alpha is equal to 0.01 because we're finding the 99% confidence interval. And we're going to use this to calculate t alpha over 2, or our critical value. We start by drawing our bell-shaped curve for the t-distribution. That middle area is equal to our level of confidence, or 0.99. And our tails, the total area in our tails is alpha, so the area in each tail is alpha, or 0.01, divided by 2, or 0.005. Using inverse t, with the area to the left being 0.005 and our degrees of freedom of 6, our critical values are negative 3.707 and positive 3.707. And for our formula, we will only use our positive value, 3.707. So now we have all of the unknowns. We're going to plug them in and simplify to find our lower and upper bounds. Again, be careful here. The denominator is the square root of n. Make sure you're not using the degrees of freedom. Our lower bound is 4,000. 4,785.186. And our upper bound is 9,297.614. And in this video, I'm not going to go over writing the interpretations. You can ask me in class or your instructor in class, but it just takes too much time. The college president asked the statistics teacher to estimate the average age of students at their college. How large a sample is needed if the teacher wishes to be 99% confident and within 1 year of the true age? From a previous study, the standard deviation of the ages is known to be 3 years. Again, what we want to start with is identifying what the question is asking us to find or construct. We're looking for how large of a sample size is needed, and we're given information about mean and standard deviation. So we know that we're talking about determining sample size when estimating a population mean. The formula for estimating sample size when estimating sample mean, or population mean, is n equals z alpha over 2 times the sample standard deviation over margin of error. And this whole quantity is squared. From our problem, we know that alpha is 0.01 because we want to be 99% confident. And notice in this formula, we're back to our standard normal, our z-score, and that is because we don't have our sample size anyway, so we can't use degrees of freedom that are required when using the t-distribution. So we're looking for z alpha over 2. Notice the process is exactly the same when we're finding a critical value, regardless if it's a z or a t-score. Our level of confidence goes as the area in the middle, and the area of each tail is alpha divided by 2, or 0.005 in this case. We're going to be using inverse norm, again, because we are now calculating a z-score, not a t-score. Using inverse norm, our critical value is going to be 2.576. The problem tells us that the standard deviation is 3. And our margin of error is going to be that statement that follows the word within. So if I'm looking at this, it says within 1 year of the true age. That's what's indicating my margin of error. Now that I have all the values of the unknowns, plug and chug. N equals 2.576 times 3 divided by 1, all being squared. This comes to 59.721, and we know that we are always going to round up to the next integer. So we need a sample size of 60 to be within 1 year of the true age. Below is the information on pulse rates for men and women. Take a minute to read the table and familiarize yourself with it. What is the best point estimate of the mean pulse rate for males, and what is the best point estimate for the mean pulse rate for females? When we're talking about the best point estimate for mean, we're going to use our sample mean, which is x bar. So the sample mean for males was 69.4, and for females, 75.9. Construct a 99% confidence interval estimate of the mean pulse rate for males. So we're looking for a 99% confidence interval for the mean, and we're focusing on just males in this example. Because we know that we're writing a confidence interval for the mean, we're going to use the formula x bar plus or minus t alpha over 2 times s over the square root of n. We know that x bar for males is 69.4. The standard deviation for males is 11.3. And the sample size for males was 41. Alpha is equal to 0.01 because we're finding the 99% confidence interval. And now we'll work on finding our critical value. The area in the middle is equal to our confidence level, 0.99. And the area in both tails combined is alpha. So the area in each tail is alpha divided by 2. Because we're looking for a t-score, we're going to use inverse t, using the area to the left and a degrees of freedom of 40. And we find that our critical value is positive 2.704. Substituting in our unknowns, we get 69.4 plus or minus 2.704 times 11.3 divided by the square root of 41. After evaluating on our calculator, our lower bound is 64.628 and our upper bound is 74.172. And again, I'm not going to write out the interpretation, but I'm going to read it to you guys. It should say we are 99% confident that the population mean pulse rate for males is between 64.628 and 74.172. Construct a 99% confidence interval estimate of the mean pulse rate for females. So again, we're constructing a 99% confidence interval for the mean, focusing now on our females. Because it's still a confidence interval for mean, we're going to use that same formula, x bar plus or minus t alpha over 2 times s over the square root of n. Again, I encourage you guys to write out the formulas. That way you know what information you need to go look for from the problem. You might have more information than you need, and so identifying what's important based on the problem that you're solving is a good thing to do. X bar for females was 75.9, and the standard deviation for females was 11.12. We had the same sample size of 41, and we're constructing a 99% confidence interval, so we still have alpha equals 0.01. Since the degrees of freedom and our level of significance, or excuse me, our confidence level or alpha are the same, then I know that my critical value is going to be the same as well, because your critical value is just based off of your confidence level or alpha and your degrees of freedom. If you're not convinced by this, you can certainly go through that same technique of drawing your curve, looking at that area in the middle, and using inverse t. I will note that it is expected that you guys are showing this process even though we're not doing it in this example. So substituting into our formula, 75.9 plus or minus 2.704 times 11.12 divided by the square root of 41, which gives us a lower bound of 71.204 and an upper bound of 80.596. Our interpretation would be that we are 99% confident that the population mean pulse rate for females is between 71.204 and 80.596. The next question in our notes is talking about the comparison between the two confidence intervals and what do the results suggest about the difference between pulse rates for males and for females. So if we're looking at our two confidence intervals, it seems pretty clear that women tend to have a higher pulse rate than men do. You wish to conduct your own study to determine the proportion of adult males aged 20 to 34 who have hypertension. What sample size would be needed for the estimate to be within 3 percentage points with 95% confidence? The question is asking us to find the sample size, and we're estimating proportion. Those two elements of the problem indicate that we're going to use the formula n equals p hat times q hat times z alpha over 2 divided by e squared. E, again, is our margin of error. Now that we know the formula we're going to use, let's go through the problem one more time to identify the values of our unknowns. Looking back through the problem, it doesn't give us anything that indicates a sample proportion of adult males who have hypertension. Since your sample proportion is not given, we will use 0.5. Q hat is 1 minus P hat, or 0.5 as well. Our margin of error, again, looking at this statement within 3 percentage points, anything following that word within is indicating our margin of error. And 3 percentage points is like 3%. And as a proportion, that would be 0.03. Alpha is 0.05 because we're looking at 95% confidence. And I'm going to use that to find my critical value Z alpha over 2. The area in the middle of my curve represents my level of confidence, so 0.95. And the area in each tail is alpha divided by 2. So total area in both tails is alpha. Each tail is alpha divided by 2, which leaves 0.025 in the left tail, 0.025 in the right tail. We're going to use inverse norm because now we're looking to calculate a z-score. The area to the left is 0.025, and our critical value is 1.960. Now that we have our values, plug and chug. 0.5 times 0.5 times 1.960 over our margin of error, which is 0.03, squared. This gives us 1067.1. Since we're always going to round up for sample size, we need a sample of 1068 males. A poll of a random sample of 2,000 Americans by the Pew Research Center in March 2002 indicated that 720 people considered themselves born again or evangelical Christians. Find a 98% confidence interval for the proportion of people that consider themselves evangelical Christians. We're asked to find the confidence interval for proportion, which tells me I'm going to use the formula P hat plus or minus Z alpha over 2 times the square root of P hat Q hat over N. P hat is our sample proportion. So in a sample of 2,000, 720 consider themselves evangelical Christians. So P hat is 720 divided by 2,000, which is 0.36. Q hat is 1 minus our P hat, or 0.64. Our sample size is 2,000. And alpha equals 0.02 because we're finding the 98% confidence interval. Going through the steps to find our critical value. The area in the middle is equal to our level of confidence, and the area in each tail is alpha divided by 2, so 0.01, 0.01. Using inverse norm, we find that our critical values are negative 2.326 and positive 2.326. And again, we only use that positive critical value in our formula. So our confidence interval is going to be found by taking 0.36 plus or minus 2.326 times the square root of 0.36 times 0.64 divided by 2,000. Carefully typing this in our calculator, our lower bound is 0.335 and our upper bound is 0.385. We are 98% confident that the population proportion of evangelical Christians is between 0.335 and 0.385. A doctor wants to estimate the mean HDL cholesterol level of males in their 20s. How many subjects are needed to estimate the mean HDL cholesterol level of all males in their 20s within 1.5 points with 90% confidence, using a standard deviation of 12.5 from an earlier study? The question's asking us to find how many subjects are needed to estimate the mean. That tells me the formula I'm going to use is N equals Z alpha over 2 times S divided by E, all being squared. S is our sample standard deviation. From the problem they'd give us, it's 12.5. Our margin of error, again following the phrase or the word within, is going to be 1.5. Alpha is 0.10 because we are looking at a 90% level of confidence. The area in the middle of our normal curve is our level of confidence, 0.90. So the area in each tail is alpha divided by 2, or 0.05. Using inverse norm, with the area to the left being 0.05, our critical values are negative 1.645 and positive 1.645. And on our formula, we'll just use that positive value. So N equals 1.645 times 12.5 divided by 1.5, all squared. Making sure that you use parentheses on that whole fraction because you're squaring that whole quantity. We get 187.9, and we're going to round up to N equals 188.